Number 1. What is fluid? Fluid. It is a substance that flows or deforms when we apply shearing forces to it. It can be liquid or gas because liquid can easily deform when stressed and it do not go back to its original shape when force disappeared. Also, atoms in liquid are in close contact but unlike solid, it can slide over one another. Fluids can move easily, that's why it's considered like gas because it's easy to compress and allows them to flow. That's what makes them fluid. Fluid can never be solid because solid resists shearing forces due to its atom that um, always in contact with its neighboring atom that made them hard to move. Number 2, example 14.1. What force must a dam withstand? So based on the problem, so we're going to find the average pressure on the dam due to the water and we're going to calculate the force exerted against the dam. So first we're going to save the average pressure due to the weight of the fluid. So we're going to use this formula which is the pressure times HPG or the depth, the density, and times the acceleration due to the gravity. So based on the given, um, our the our h or the depth is equals to 40 meters and the density, we're going to get the density of water from the table 14.1 which is 10 10 raised 10 cube kg per meter cube times the acceleration due to gravity which is 9.80 meter per second squared. So um, the answer would be 3.92 times 10 raised to 5 Newton per meter cube, and we all know that 1 Newton per meter cube is equivalent to 1 Pascal. So we can say that the pressure is equals to 392 kilopascal. And now, since we have the pressure, we can now solve for the force exerted against the dam. So first, to get the force, we're going to solve for um, the area of the dam. So first, since in the given we have the wide and the deep of the dam, so we're going to multiply 80 meter times 500 meters equals to 4 times 10 raised to 4 meters squared. So therefore, since we're going to use the um, this formula which is force is equals to pressure times area, so let's substitute the value. So pressure is equals to 3.92 times 10 raised to 5 Newton per meter squared times area which is 4 times 10 raised to 4 meters squared. So the force exerted against the dam is equals to 1.57 times 10 raised to 10 Newton. Number 3, example 14.3. Calculating force on wheel cylinders. Pascal puts on the brakes. So based on the given problem, so our given is our F1 or the exerted on the pedal cylinder is equals to 500 Newton. So our cross-sectional area number 1 and 2. So I'm going to explain that later. So what are we trying to find here is the F2 or the magnitude of the force that created at each of the wheel cylinders. So solution, we're going to use the Pascal principle applied to hydraulic system which is the equation 14.12. So F1 over A1 is equals to F2 over A2, and since we're trying to find the F2 or the magnitude force that created at each of the wheel cylinder. So by simple manipulation, we're going to cross multiply, which is may muna siyang F1 A2 is equals to F2 A1, and since we're trying to find the F2, we're going to divide both sides by A1. So thus the equation is equals to F2 is equals to A2 over A1 times F1. So we're going to substitute the value of the the area. So, di ba, area is equals to pi r squared. So, based on the given problem, the um, the area or the radius na binigay, I mean diameter na binigay sa A1 is 0.500 cm, which is the pedal cylinder. That's for A1, and since we're trying to find the radius, so radius is equals to diameter divided by 2. So we're going to divide the diameter. So let's find first the A1, which is 0.500 cm. So 0.500 divided by 2 is equals to 0.250. Now for the A2 or the each the value of each wheel of the cylinder is 2.50 cm. So 2.50 cm divided by 2 is equals to 1.25 cm. So now we have the value of the cross-sectional area, which is 1.25 cm squared and 0.250 cm squared. So cancel na ang pi. Pero bisag napaghihapon na, same ra gyapon ang answer. So 1.25 cm squared divided by 0.250 cm squared is equals to 25 times 500 Newton. So our magnitude of force created at each of the wheel cylinder is equals to 1.25 times 10 raised to 4 Newton. Number 4. Example 14.4. Calculating average density. Suppose a 60 kilogram woman floats in fresh water with 97% of her volume submerged, where her lungs are full of air. What is her average density? So, based on the given problem, we're going to find the density of the woman or the person. So let's say this is the density of person. So solution. So we're going to find the density of a woman by solving the equation fraction submerged is equals to the density of object over the density of fluid. So we all know that the density of an object is equals to the density of a person. So let's say the by manipulating the this equation, where we can have the density of a person is equals to the fraction submerged times the density of fluid. So since we know the fraction submerged and the density of water, which is 10 cube kg per meter cube, based on the table 14.1. So let's solve. So the fraction submerged is equals to 0.970 times the density of fluid, which is 10 cube kg per meter cube. So the density of the woman or the person is equals to 970 kilogram meter cube. So since the woman floats, so we expect that the woman density is less than the fluid density. Example 14.5. Calculate fluid speed through a nozzle. So a nozzle with a diameter of 0.500 cm is attached to a garden hose with a radius of 0.900 cm. The flow rate through hose and nozzle is 0.500 liter per second. Calculate the speed of a water A in the nozzle and B in the A in the hose and B in the nozzle. So in this problem, we're going to find the speed of water in the hose and in the nozzle. So we're going to put the speed of the water in the hose as in subscript 1, and the speed of water in the nozzle is to subscript 2. So first, let's find the speed of water in the hose, which is we're going to use the subscript 1. So um, we can use the relationship between flow rate and speed to find both speeds. So we can use the subscript 1 for hose, um, subscript 1 for hose, and subscript 2 for the nozzle. So now we're going to solve for the flow rate equation for speed, and we're going to use the pi r squared for the cross-sectional area of hose. So um, the average speed is equals to um, flow rate over the cross-sectional area. So we're going to substitute the value of area is equals to pi r squared. So this for the subscript 1. Now substituting the value of the substituting the value, and we're going to use the appropriate unit conversion. So the flow rate again of the hose is equals to 0.500 liter per second. So time E, we're going to multiply it to the 10 raised to negative 3 meter cube per liter, and divide by the cross-sectional area, which is 3.14 times the um, radius of the hose, which is 0.900 cm, times 10 raised to 3 meter squared. So the speed of water in the hose is equals to 196 meter per second. And for the um, speed of water in the nozzle, so we could repeat the same calculation to find the speed in the nozzle, but we're going to use the equation continuity to give somewhat different insight. So the equation states A1 V1 is equals to A2 V2. So since we're going to solve for V2, so by simple manipulation, we're going to divide both sides by A2. So our final equation will be V2 is equals to A1 over A2 times V1. So we're going to substitute now the value of the area, which is pi r squared. So it will become pi r squared over pi r squared times V1. So cancel both the pi. So we have now r r squared over r squared times V1. So substitute the value. The value of our cross-sectional area subscript 1 is equals to 0.900 cm squared, and for the cross-sectional area of our subscript 2 is equals to 0.500 diameter, and divide 2 to get the radius. So it become 0.250 centimeter squared. So we're going to multiply it to V1, which is 1.96 meter per second. So our V2 or the speed of water in the nozzle is equals to 25.5 meter per second. Number 6, example 14.7, calculating pressure, a fire hose nozzle. So based on the problem, so we're going to find the pressure or the P subscript 2. So since the depth is not constant, so we're going to use the Bernoulli's equation to solve for the pressure. So Bernoulli's equation is equals to P1 plus 1 half density times the velocity squared for subscript 1 plus density times the gravity and height is equals to P2 plus 1 half density times velocity squared for subscript 2 plus PGH for subscript 2. So first we must find the speed or the velocity subscript 1 and V2. So since the flow rate is equals to the um, area times the velocity, so we're going to solve first for the V1. So V1 is equals to flow rate over cross-sectional area subscript 1. So substitute the value. So flow rate is equals to 40 times 10 raised to negative 3 meter cube per second. So for cross-sectional area subscript 1 is pi, and times the radius, and since in the given it is in diameter, so we're going to divide it by 2 in order to get the radius, which is 3.20 times 10 raised to negative 2 in order to convert it into meters. So the answer would be for the velocity subscript 1 is equals to 12.4 meter per second. So same with v squared. So v velocity subscript 2 is equals to flow rate over area is equals to 40.0 times 10 raised to negative 3 m cubed squared divided by pi times 1.50 times 10 raised to negative 2 m squared. So we're going to get the 56.6 meter per second now. So we're going to solve for the Bernoulli's equation for pressure subscript 2. So P2 is equals to P1 plus 1 half times density times V subscript 1 squared minus V subscript 2 squared minus density times gravity times the height or the depth. So substituting the value, so P1 is equals to 1.62 times 10 raised to 6 Newton per meter squared plus 1 half times the density, which is 1000 kilogram per meter cube, times the velocity of subscript 1 squared, so 12.4 meter per second squared minus 56.6 meter per second squared minus the density, which is 1000 times the gravity 9.80 times the height, which is 10 meter. So our pressure in subscript 2 is equals to 0.